and be able to help here with this. Okay, it says from the graph, determine the time at which Derrick has the largest lead. So the largest lead means the maximum difference in distance, not velocity. Okay. Yeah, so the short answer here is that we have to figure out the difference in the areas under the curve from 0 to 6, because at 6 is when their velocities intersect.
Right.
And so let me I guess show that up here. So the distance traveled by the first person. Let me see. I'm sorry, just getting my bearings here. This is so weird. It's a little awkward, this question. They're trying to make something out of it. So so the distance traveled by Derrick is the integral from 0 to 6, 10t minus t squared dt. That's this area under the curve.
Okay.
And the distance traveled by John, is also the integral from 0 to 6, but this time it's 4t dt.
And then do you just take the difference of those integrals?
Yes.
Okay.
So you can actually do one integral to do the entire question.
Right.
If you want. Doesn't matter to me, but I would probably do them all. I would do it all together. So it's 0 to 6, 10t minus t squared minus 4t dt, and then I would actually simplify. So this becomes 6t minus t squared in here, and that's what you're integrating. So the antiderivative of this is 3t squared minus 1/3 t cubed evaluated from 0 to 0 to 6. So if you take the derivative of both of these, you get back to the original, and then you just have to do top minus bottom. So it's 3 times 6 squared minus 1/3 6 cubed. 6 squared is 36, times 3 is 108. 6 cubed is 216, and then 1/3 of that is what, 72? So that equals 36 meters.
Okay. And the reason the integral, or not the integral, the interval is from 0 to 6 is because that at 6 is when they meet.
Their velocities are the same.
Oh, okay.
So if you were the faster runner and I was the slower runner, you would be further, you would create a further lead. Your lead would get greater as we ran. But as soon as I catch up to your velocity, and let me put it another way. If you start a race before me and you get out some distance, doesn't really matter, and then I immediately get up to the speed you're going, I never catch up to you.
Right. Because
we're running at the same speed.
Right.
So the only way I catch up to you is if I start running faster than you.
Right.
And this graph up here, what it shows is that Derrick is running faster than John all the way to this point. So he's always going to have gone further than John because his velocity is greater.
Right.
But as soon as their velocities are the same, the distance between them goes to 0. But notice that John's velocity continues to increase. So he actually catches up and probably even passes Derrick.
Right. Okay. All right.
Okay. So you probably have to put some words with that.
Or it says determine the time at which Derrick has the largest lead.
And that's at 6.
So it would just be 6.
Yeah, we actually did way more than we needed to on that one. I'm sure we have to do this, but it is at 6. And it's at 6 because that's when that's when their velocities are the same.
Okay.
Yeah, thanks for catching that, because that would be a problem. Shade the region between the two curves, determined in part one, and then so what we did is actually part two here. Everything above this, all of this work up here is part two.
Oh, okay. Okay, all right. So number one, how would you explain why it's at 6? I'm sorry.
Yeah, let me grab it again, and I'll type a few words here that you can choose to change if you want. So let me insert. Where's my typing thing? Okay. The at time t equals 6. Is it seconds, minutes?
Probably, it's probably seconds. It actually doesn't say.
Minutes.
Oh, it is. Never mind.
At t equal, okay, so t equals 6 minutes. Both Derrick and John have the same velocity. For t equals 0 to t equals 6, Derrick always has a greater velocity than John, meaning that he is covering more distance.
Okay.
Once their velocities are the same, the distance between them no longer changes at that instant in time. I don't recommend copying that. It reads very formally, like you got it from someone.
Uh-huh.
So I would recommend rewriting that slightly,
Okay.
reorganizing it, somehow changing that
All right.
also. So let me increase the font size here. On that, let's go 14, 16. Yeah, it's probably a little more readable.
And then number 2 is the work we just did.
Number 2 is the work we just did. And now we can do 3. Number 2 also includes this graph that's shaded in.
Uh-huh.
Make sure you show that. And hopefully intuitively, like you understand, if someone is running faster than you in a race, you have to run faster than them at some point to catch up to
Right.
them.
Right. Yeah.
Pass them. Yeah. And this is not where they pass. This is just where their velocity is the same. That's where you start gaining ground on them. It's not until a later time when you actually catch them.
Right. And the area would be 36 meters squared. Just want to be clear.
That's the distance. It's just distance is just meters.
It would be meters squared since it's the area.
Oh, the area is 36. Good. I'm glad you're asking, because to clarify, I'll clarify what I said. The area is 36, but what it means is the distance is 36 meters. So the area, we got to be careful. The area is 36.
Uh-huh.
And then when it puts it into context, we can actually answer that. But
okay. I think so.
The area is 36. Don't put in meters there.
Okay. All right, that makes more sense.
Number 3. Okay, so explain in complete sentences what the area of this shaded region represents in terms of Derrick and John's distance traveled. So before we can do that here, let me just draw this and then draw this. So this is Derrick and this is John. Okay, and is it clear that these are meant to represent the kind of the individual sections? Okay, so on the left is Derrick's distance traveled. On the right is John's distance traveled. That's what they mean. So let me type some of that, because you might even want to include this in your explanation. So
Okay.
on the left, the area of Derrick is shown, and this represents his distance traveled. Similarly, John's distance is, or John's area, similarly on the right, I guess we're going to follow the same format here. On the right is the area of John, and this represents his distance traveled. Sorry for all the typos here. I'll clean that up in a moment.
That's fine.
So the shaded region, which is referring to this back here,
Right.
this is what you need to show in part 3. Let me make it a little smaller, but you want to show this with the shading over here. Then you want to say the shaded region represents the distance Derrick is ahead of John in the race. That didn't go, that didn't move. There it is. Okay. Let me know when I can move on to the next.
Yeah, you're good.
Okay. 4. Now shade the region between the two curves, between the time in 1 and the time in 10 minutes. So basically, we're going to go back to this drawing here again. And this time, let me do it. We're going to do a different color here. The color blue is going to represent the distance between the two curves. So it's this right here. All of that.
Okay.
And then it wants us to find the area of that shaded region. Okay, so this is the integral from 6 to 10, because you're starting at 6 and you're going to 10. And then the top this time is 4t. And your bottom,
why are you starting at 6?
because you're that's where they intersect. It says from the time in 1 in
Oh,
question
okay,
1.
okay.
Yeah, and that's we normally have to calculate that. They just give it to you.
Okay, yeah, that's fine.
And then it's top minus bottom. So the bottom curve is 10t minus t squared. dt. So again, what I would do is I would combine like terms here.
Right.
4t minus 10t plus t squared. So I would write this as t squared minus 6t, and that's what you're integrating. So that's 1/3 t cubed minus 3t squared evaluated from 6 to 10. And this time you actually do have to put in both bounds. So it's
Right.
1/3 10 cubed minus 3 times 10 squared minus parentheses 1/3 6 cubed minus 3 times 6 squared. So this first one is 1,000 divided by 3 minus 300. And on the right, we actually already did this calculation, but we can do it again here. It's 6 cubed 216 divided by 3, that's 72. 6 squared minus 108. This should look really familiar. That's the 36.
Right.
but it's negative, and then it's positive. It's plus 36. So plus 36. And so we got 300 over 1. So that's really 900 over 3, 1000 over 3. So that becomes 100 over 3 plus 36 over 1. So over 3, that's 108. I'm sorry, that's, yeah, 108 over 3. So this becomes 208 over 3.
Alrighty.
Is this okay? Is this all clear?
Yes. Yep.
Okay. All right. So there's a way to answer 5 with the information we've already answered, but we're going to do 5 differently to make it like really clear how to do this.
Okay.
So we want to know the distance of the two people. So the first guy, Derrick, we want to integrate from 0 to 10. And then his function, what was it? 10, was it 10t?
It was 10t minus t squared.
dt. Okay. So we're going to find the anti-root of this. It's 5t squared minus 1/3 t cubed. And we're going to evaluate from 1 to 10. So that's 5 times 10 squared minus 1/3 times 10 cubed. So that's 500 minus 1000 over 3. So that's really 1500 over 3 minus 1000 over 3, which is 500 over 3. And that's how far Derrick went. He went 500 over
Right.
3. Okay. Now we're going to do the same thing for John. So John is the integral from 0 to 10, 4t dt. So this is 2t squared evaluated from 0 to 10. So it's 2 times 10 squared, which is 200. Is that right?
All right.
Is that right? Yeah, I guess that's right.
Yep.
Okay. So 200 in terms of this is like, it is, if we do it over 3, is 600 over 3. So
Right.
who covered more distance?
John did.
John did. Okay. And so that, like, we can answer it now with some full sentences. So you could say that in the race, Derrick covered a distance of 500 over 3 meters. Oops. And John covered a distance of 200 meters. You could throw in parentheses, that's 600 over 3, indicating that John won the race because he covered more distance in the same amount of time. Oh, we have to say in how much also, so we can add that in here. So John won the race by 100 over 3 meters. We just throw the calculation there.
Alrighty.
Now, we could have gotten that answer another way, but let me see here. Yeah. Is this okay? Does it
Yep.
like does that good enough for you? Okay. All
That's
right.
good.
Now the kind of the I'll just, this is sort of an aside here. You win the race because you get there fastest, not because you covered the most distance.
Right.
You could also point that out to your instructor and say, not trying to be difficult here, but when we run every day, and the person who gets there first, it's not the person who covered the most distance.
Right.
And but there's another way to do this, where you could actually figure out where they covered the same distance and stopped. But that's a more advanced problem, I guess.
Okay.
Maybe that's why your instructor didn't have it here. So
Alright. Yeah, I guess we're done with that. I'm gonna get my notebook real quick.
okay.
Just use the rest of the time. I also have an appointment scheduled for tomorrow.
Okay.
Over to go over volumes of shapes.
Oh boy. Okay. Yeah, there's a lot there.
Yeah, there is. But I guess. Does the washer's method sound familiar?
Yeah, there's disc and washer.
This could, yeah,
There's x-axis and y-axis problems. There's offset. There's a lot of problems there. It's
yeah. I need to know the difference between disc and washer, and like when to use them.
okay. So we can actually start with this problem right here. Kind of this one right here, if that's okay.
Okay.
Just grab this.
It's like 3D objects. She's drawing them on the board and stuff.
Yeah, hopefully you're not drawing them too much.
Yeah, I'm
Okay.
drawing them in the notes, but
Yeah. So if you take
hopefully
any
I'm
computer
drawing.
aided design classes, I mean, that's how you create a solid, is you rotate it.
Right. Yeah. Yeah, I have.
Okay, so this right up here, if you were to revolve this around the x-axis, which is over here,
Yeah.
you get a solid. Okay, and it's a disc. It's a disc because it's big R squared minus little r squared. I'm sorry, is that right? Maybe you find the difference between them. Sorry, let me go look. I've done one of these.
I think we do R2 minus R1 if that is.
Sure, we can do that. Let me
Oh,
get.
actually, yeah.
Um, so they sometimes call these, rings. Rings, washer. Okay, so you're using are you using big R, little r? It really doesn't matter, but what are you using? I'll try to be consistent. Little r.
There's some big R's on my notes, but
Okay, well, let me try to get you to use big
just
R and
do it,
little
yeah.
r.
Just go ahead.
Okay,
Yeah.
and you go from A to B. Okay, so in this drawing here, and actually I'll add some color. I think that'll help here. If big R is red, big R is the distance from the x-axis to that. This is big R.
Okay.
And little r, I'll show that in blue. Little r is in blue here. That's the distance from the axis to the bottom one. And it's good to draw these. Okay, so those are both equations. So big R in your problem, your big R is, actually, let me switch colors, is the 10t minus t squared.
Right.
That's this curve. And then little r is the other one. The other one is 4t. So you take these, and there's a pi. Let me add this.
How would you identify which one is big R, little R? Is just which one that goes up higher?
Whichever one's further, yeah.
Okay.
It's always top minus bottom.
Okay.
Okay, so now these go in here. So this goes in here, this goes in here. So it becomes, excuse me, the integral from 0 to 6 pi 10t minus t squared minus 4t squared dt. Just, that's big R and that's little r.
Okay.
Now, do you have to do these by hand?
Yes.
Okay. So you almost always bring the pi out. Pi just comes along for the ride here. You have to remember some stuff from previous courses, like how to multiply these together. And you got to be fast because that's not really what they're emphasizing here. You got to be able to FOIL this. So it's 100 t squared, okay, minus 20 t cubed plus t to the fourth minus 16 t squared.
Now, is this a washer example?
Yes, washers have big R and little r.
How do you identify if you need a washer or to use washer or not?
If there's a gap, say there's a gap between the axis and
And the line?
the region that you're
Yeah,
rotating.
okay. So what is okay, no, I'll just ask you after you're done.
No, I mean, please ask. I mean, like it's really complicated. I
I was
mean,
gonna ask what's the
visually.
difference between a washer and disc?
Uh,
Or is disc when you're reflecting across the
sorry, this is the washer method, not disc. Washer or ring.
okay,
So they have. I mean, it's the donut.
right.
That's what these are. They're donut problems. And then the disc is it's kind of it's the solid one. I don't know. Discs have a hole in the middle, so it's kind
Is
of
it
better.
when you reflect or revolve or whatever across the y-axis?
No, because you know that's different. There's okay. So let me quickly give you an example of, let's say I want square root of x and I want to revolve this around the x-axis, and I want to do this from 0 to 9. This is a disk because there's no gap between the axis. See how it's completely solid all the way to the axis?
Right, okay.
So the disk is integral r pi r squared from a to b.
So when there's one function, that's when you do disk?
Generally, yes.
Okay.
Okay, now to answer your question, there's disk and there's washer problems, and then there's x-axis problems, and then there's y-axis problems.
Okay.
Now there's also this thing called the shell method.
Yeah, we
Heard of
just
that?
learned that today.
Okay, and that's throws another little thing in here. So like you want to be comfortable doing, like you want to check the box here and say, oh
Right.
yeah, I know how to do each of those. Now x-axis problems, and I'm probably throwing way too much at you. There's also problems where you do y equals a number, where you revolve around that.
Uh-huh.
And
Right.
then there's also x equals a number problems that are like y-axis
Yep.
problems.
Yeah, we've done
Okay.
that.
Okay. So you got them all kind of covered here.
Yep.
Okay. So like truly, like everything from this point forward is like review. Just to like the hard part is setting them up.
Yeah, I just need to learn to set them up. I can integrate forever.
Okay. Do you have some problems that you can send me from homework that we could work through, or would you like me to find some?
Yes, it'll take me just a minute.
Okay.
Because I guess my main problem is identifying like what to use, like which
Sure.
thing to use. But let me go to this.
So the exam will tell you to find the area of the volume. And you may get the choice of which one to use, but there might be problems where it says like you must use the shell method in this problem, or you must use the washer
Right.
method. So you should be prepared for that and not.
Yeah, she said she'll tell us which technique to use.
Sometimes they say things like,
But
"Oh, it'll be
sometimes they won't.
obvious when you see the problem," and it's
Yeah,
not.
right.
It's not until
Exactly.
you've done it a few hundred times.
Exactly. I guess this is 7. Yeah. Okay, I think I got some. Okay, we can see these right here. All right, I just sent right now.
Yeah, I got it here. All right, anything, so I think we should do y-axis problems. Those seem to
Okay.
be the most difficult problems for students. So let me start with 8. Is that okay?
Yep, that's fine.
Okay. So another thing that happens here for students is that you have to actually graph stuff, and you maybe not any good at that, and that's that comes out here. So you can use Desmos like for practice, but you do want to get good at graphing things. So here's x equals 2. And then it doesn't have to be very perfect, but 1/4 x squared, it hits somewhere here. So when x is 2, that's 1. So you got a curve that looks like this, and they want to revolve this region y equals 0. So this little slice here about the y axis. So this filled in area here about the y axis. So you have a choice here. Let's just use the in this case, we're going to use the washer method. And the reason is there's that gap between like there's this empty space here between it and the y-axis. So when you're doing the y-axis, it's right minus left. So you heard that in class.
Yes.
Okay. And then you actually need to solve this for y. I'm sorry, solve for x. Because you're gonna integrate with respect to y.
Yep.
So it's y equals 1/4 x squared. X equals the square root of 4y, which you can reduce to 2 square root y. Okay, so the big R, actually, I kind of need to blow this up here. So your big R, let me make this bigger here, and there's your axis. Your big R, grab another color here. And I really do recommend drawing it is this right to here. This is your big R. And then your little r is this one there.
Okay.
So just to summarize here, the volume is the integral pi big R squared minus little r squared. In this case, it's dy because we're going around the y-axis.
Yeah.
And we've got to find our limits here. So you need this y value and this y value here. Well, obviously this is 0, 2, or I'm sorry, 2, 0. Okay, so your y value is 0, but this one actually is 2, 1. And the way you get that is from plugging 2 into this equation up here.
Uh-huh.
So that gives you your bounds. So you got to find your bounds 0 to 1, pi. Oh, and that's another thing. So sometimes they just ask you on the exams to set up the integral and like
Right.
either match it or just set it up and not actually to do it
Uh-huh.
on all the problems, because you can see they're very long. So big R, in this case, big R is, and sometimes you write it there, big R is 2. It's always 2. Like it doesn't matter where you are, your radius, your big R is always 2. Your distance from the y-axis to this line is always 2.
Okay.
So that's 2 squared minus, now little r changes. Little r is this
Yeah.
function here. It's 2 square root y squared. Little r is 2 square root y. Is that okay?
Yep.
All right, so then just a little bit of work here. Pull the pi out. 4 minus 4y dy. So this one's not too bad to integrate. 4y minus 2y squared, evaluated from 0 to 1, and then you got a pi also coming in there.
So when you're rotating about the y-axis, you want your intervals, you want it to be
It's on the y-axis.
on the y-axis.
Yeah.
Okay.
So multiple choice is not your friend here because
Yeah.
you can get the right integral with the wrong limits or so on. It's awful. So this chart,
We
I
don't
was trying
have
to show
any
you,
multiple choice.
what with this chart is that you like want to know those things. You want to be like, oh yeah, I have to, when I do it around the y-axis, I have to solve for y with the
Right,
disk
yeah.
and the washer method, but it's not that for the shell method, which we can get to at a little later time. Maybe
Yeah, I want
tomorrow.
to do the disc and washer.
Yes. Okay, so we should do like a 10. Is 10 okay?
Yeah, that's fine with me.
Okay. Okay. So you gotta graph this thing. Y equals e to the minus x. Y equals 1. What's the other one here? X equals 2. About the line y equals 2. Oh, I'm sorry. That's not the right axis. We're not going to do that one because it's well, okay. Let's do it. It shouldn't say that. So here's the line y equals 1. And here's x equals 2. And then e to the minus x. So when you put 0 in for x, you get e to the 0, which is 1. When you put 1 in, it's 1 over e. So it's kind of down here.
Uh,
Hope that's not too small, but it's this region right here. But this time you're revolving it around this line up here.
uh-huh.
It's because it's parallel to the x-axis. That's an x integral.
Okay. So this is what you want to use the washer method here again.
Yes. Now you got to be able to draw your big R and your little r. So it's your big R this time is to this bottom curve.
All right.
That's your big R. Your little r is to the top one there. That's your little r. Hopefully that's visually okay.
Yep.
So now this is the tough part is when you've got the integral pi big R squared minus little r squared. Okay, great. So what is your big R? Well, your big R is normally, I really almost need to zoom in on this, but normally the function, so this e to the minus x gives you the distance from the x-axis to this point.
Right.
But we want the distance up here, so it's 2 minus e to the minus x.
Right. Yeah. Okay. Right.
Okay, and it's always that. Now, one thing you could do is test the endpoints to make sure it works, but that does work. Okay, and then little r little r this time, it's always, well, in this case, it's 2 minus 1 because you're already up here at 2 and you subtract 1, but it's always 1 because that gap never changes.
Right, where does the one come from?
So it's like it's kind of the same principle here. That like this one is 2 minus, this one is 2 minus. The thing you're subtracting is the distance from the x-axis there. Let me try and draw here. So in the first one, this is that green part, and in the second one, it goes all the way up there to 1.
Okay. Oh,
So-
okay, right, I get it.
Great. All right. I need to make a bigger drawing. So we're going to integrate from 0 to 2 because that's our x-axis this time. So it's integral 0 to 2 pi parentheses 2 minus e to the minus x squared minus 1 squared. And this one we should do just a tiny bit of work here. If you remember a minus b squared, it's always a squared minus 2ab plus b squared. So this is 4, and then you squeeze them together. So it's minus 2 e to the minus x, then you double it. So it's minus 4 e to the minus x. When you square this last term, it becomes positive. That becomes positive. And then the exponent actually multiplies what's inside. So it's e to the minus 2x, not squared. That's a mistake on this.
Okay.
So this is integral 0 to 2, pi's out here, 3 minus 4 e to the minus x plus e to the minus 2x dx. Okay, now you gotta find your antiderivative. So it's 3x plus 4 e to the minus x minus 1/2 e to the minus 2x, evaluated from 0 to 2 times pi. Let me know if there's anything on this you want me to cover.
No, that's
Okay.
fine. Yeah.
Okay, so this one, you do have to evaluate at both endpoints. 6 plus 4 e to the minus 2 minus 1/2 e to the minus 4 minus pi 3 times 0 plus 4 e to the 0 minus 1/2 e to the 0, because e to the zeros are not 0, they're 1. And so this is 4 minus 1/2 on the right here. So that 4 is 8 over 2 minus 1/2, 7 over 2. So it's 7 over 2 pi. We'll leave the pi there for a moment. And you got this, there's a minus there, 6 plus 4 over e squared minus 1 over 2 e to the 4th minus 7/2. So a little cleanup here. This is 12/2, so it's pi. There's a pi here. 5/2 plus 4 over e squared minus 1 over 2 e to the 4th. This answer doesn't mean anything, meaning like I don't know how big that is. I mean, if you look at our image, it's not that big, this area, but sometimes you get these answers and you have no way to know whether they're reasonable or not.
Right.
You just have to trust the work you did. They're kind of all the same. It's kind of like once you figure out which axis you're rotating about or what line, you go back to figuring out big R and little r every time. And then you do the integration, which could be easy or hard.
Okay. And then this was all washer.
Yeah.
Okay.
So we didn't really do a disk problem.
That's fine.
I mean, disk problems are always nice. They always kind of like, give you a region with the axis.
Yeah.
This would be an x-axis, or think of something like this. They give you a nice solid with the axis. There's no gap. I mean, you've probably seen a washer before. There's a gap.
And then would you just take the integral of the function?
Yes, squared. So these are always integral pi r squared.
Oh, right. Yeah.
And what sometimes happens here is you get like somehow the problem will be something that you can never integrate. Like you don't know how to integrate this, but then because it's the integral of pi square root of 1 plus x squared, all of a sudden you can.
Yeah.
So it like at first glance, you might think, oh, I can't do this, but because you square, you generally get something that does work out pretty nicely.
Okay.
All right. Is it okay if we stop here for tonight?
Yep, that's good. I got
Great. So,
got another one tomorrow.
okay. Thanks so much, Trenton. I'll see you tomorrow. Have a great night. Bye
Yeah,
now.
you too.
Bye.